Hello, everyone. My name is Noeen. I am a Director of Communications and Events at SCWIST. I welcome all of you here in our symposium session. It's the round 2 session, and we have first talk in category of particle physics today. Okay. Before we go, I would like to give land acknowledgement. We would like to take a moment and reflect on our connection to the land and thank the traditional guardians of that land, which we at SCWIST Vancouver live and work. Vancouver is on the unceded, ancestral and traditional lands of Musqueam, Tsleil-Waututh, Seychelles, Squamish, and the indigenous people of Turtle Island. Today we have first presentation in the category of physical science and particle physics. Is the round 2 competition of our national competition for women in STEM across Canada. And there are some housekeeping rules. Please note that this video will be recorded and I will upload it to the SCWIST YouTube channel by tomorrow or Friday. You can always visit our channel and watch this session again. Please keep your mobile silent and also your microphone silent, muted. And chat box will be monitored. So if you have any question during the talk or after the talk or during panel discussions with judges, please drop your questions in the chat box. We will take during question and answers from audience session. Our judges, we have our two very well accomplished scientists today with us, who will be the judges of this particle physics category. One is Dr. Otilia Ducu. She is the Senior Research Fellow from CERN, Switzerland. And we have Dr. Nedaa-Alexandra Asbah. She is the postdoctoral student from Harvard University, USA. We have our speaker, 𝐉𝐔𝐃𝐄𝐑. She is from TRIUMF and UBC, Canada. Her title of presentation is Measurements of Higgs-Boson Cross-Sections at the Large Hadron Collider. Okay. This session is sponsored by Admire Bioinnovation, Microsoft, Equitas Therapeutics, Northeastern University, Vancouver, AppSelra, Six Sense Strategy Group, Molly Surgical, and so forth. I would like to say a few words about our sponsors, what they do and what they offer. For Northeastern University, Vancouver, they have 95% employment rate for biotechnology category. In addition, they also have artificial intelligence and machine learning department, which is growing very fast. From Admire Bioinnovations, if you want to polish your skills in business or life science, please check their programs at Admire Bioinnovations Academy. From AppSelra, they have recently discovered an antibody that neutralizes the viral variant of COVID-19. Equitas Therapeutics, they have a recently new discovery. They provided their lipid nanoparticle delivery system, which is a key element in the development of Pfizer's vaccines. Microsoft, as we all know, they offer lots of internship programs in the IT. You can check their website today and see which opportunity you can avail. From here, I will stop sharing my screen and I will give the floor to Neda and Otilia to introduce themselves. And after that, Robin, you can go ahead. Thanks everyone for joining us. If you have questions, please drop in the chat box. Thank you.
Hello, everybody. From France, Switzerland. I'm a Romanian particle physicist involved in high-energy collider experiments, specifically the ATLAS experiment, since 2011. And I conduct searches for supersymmetry and non-standard Higgs boson. Basically, I'm interested in any science of new physics. And I also study the detector performance aspects related to the charged leptons and, of course, to their environment.
All right. Hi, everyone. I'm Nedaa-Alexandra. I'm currently in Mont-Tremblant. I work for Harvard University. I've been on the ATLAS experiment since 2013. I first joined when I was a student at Université de Montréal. And then I moved to Europe for my PhD, lived in Switzerland for a long time. I worked on the production of Higgs boson in association with the top quarks. That was my thesis topic. And then I've been a postdoc at Harvard since 2018. I'm mainly working on top related physics, rare processes. Recently published evidence for top quark production. So it's an exciting time analyzing run 2 data at the LHC. And yeah, I'm looking forward for the session.
Okay, thanks very much. So I'm Robin. I'm a graduate student, as mentioned, at UBC and TRIUMF. So I'm living in Vancouver, BC. I have been working on the ATLAS experiment for the duration of my kind of master's and PhD work after undergrad in Ontario. And that will today form what I'm talking about. So I think with that, I'll probably just start sharing my screen. And after doing that, I will put it in the correct view. Okay, and then if no one stops me, I will believe that this is sharing correctly and I'll begin. So yeah, thanks so much for being here today. I'm going to tell you a little bit about my work characterizing the Higgs boson at the Large Hadron Collider. Okay, perfect. So as I'm sure you know, the discovery of the Higgs boson in 2012 made headlines around the world. And this is for good reason, since the Higgs boson is the most recent and the final particle predicted by the Standard Model to have been discovered. So the Standard Model, this incredibly successful predictive theory of particle physics, really relies on the existence of the Higgs boson. So confirming that it was there was really important. Now, as we know well, the Standard Model isn't complete even with the Higgs. So it offers no compelling candidate for dark matter. It doesn't include gravity. It doesn't predict neutrino masses, among others. And because the Higgs boson plays such an important role in the Standard Model, studying it gives us a path to improving our understanding of fundamental physics. So in particular, measurements of the Higgs boson can test the limits of the Standard Model and potentially reveal signs of new physics. So the story of the Higgs boson really continues today, and that's what we'll talk about. Now, of course, to study the Higgs boson, we need to create Higgs bosons. And this is possible at only one place in the world, the Large Hadron Collider, or the LHC. Now, at the LHC, 2 beams of protons are accelerated in opposite directions, and then they're collided at a center of mass energy of 13 tera-electron-volts. These collisions take place at 4 places around the LHC ring. And one of those points is surrounded by the ATLAS detector, which is this multi-purpose particle detector that's designed to allow us to detect and reconstruct the products of the collisions. We have bunches of protons that collide in the ATLAS 40 million times a second. And it's the data that was collected using the ATLAS detector between 2015 and 2018 that we'll use to do the research we'll talk about today. Now, the Higgs boson is produced in the interaction of other particles. And there are many of these so-called production modes at the LHC. The dominant one at the LHC is called gluon-gluon fusion, or GGF, and it's shown in the red box here. Another important production mode is vector boson fusion, or VBF, which is shown in the orange box, and that's where 2 W or Z bosons fuse to give a Higgs boson. Now, after the Higgs is produced in one of these pathways, it decays in 10 to the negative 22 seconds. And so this means that we can't detect the Higgs boson directly. Instead, we look for particles that are produced in its decay. So for this work in particular, we chose its decay to 2 W bosons. This is the second most probable decay pathway of the Higgs boson. W bosons themselves are actually also too short-lived to detect directly. So in fact, we looked for their decay to leptons, meaning electrons or muons here, and to neutrinos, which is distinguishable from the big kind of quark and gluon background at the LHC. Now, our goal here will be to measure the rate of Higgs production in the GGF and the VBF production modes, which we'll usually call channels, by looking for the Higgs decay to 2 W bosons. Now, we refer to this rate as the cross-section of Higgs production. This quantity is predicted by the Standard Model for both of these production modes, so we can compare what we get to our prediction. And for this talk in particular, we're going to focus on how this is done in the VBF channel for 2 reasons. First of all, this particular combination of VBF production followed by Higgs to WW decay hadn't previously been observed by the ATLAS experiment. Also, it has theoretical importance. It involves 2 points of Higgs weak boson interaction, one in the production and then one in the decay. And so this makes it really sensitive to the Higgs weak boson coupling, which is a parameter predicted by the standard model. So measuring this cross-section can allow us to precisely test the standard model. All right, so here's our chosen process: VBF production of a Higgs followed by decay to 2 W bosons, and we call this our signal. Since this is what we want to look for, it's really important that we can distinguish it from all of the other physics processes taking place at the LHC, which we'll call our background. Luckily for us, it does have features like that we'll run through here. So on the left-hand side of this slide is a real VBF Higgs to WW candidate event that was recorded in the Atlas detector in 2017. And then on the right is kind of a diagram of our signal event and a breakdown of some characteristics that we can use to distinguish it. So first I mentioned that we'll use the W's decay to 2 leptons. We'll choose 1 electron and 1 muon, and we'll require that our leptons have opposite charge because the Higgs itself is neutral. You can see the nice clean signature that these leptons leave in the detector. So the track of the muon is in blue and the electron is in yellow there. The process also has at least 2 jets, these kind of quark lines. You can think of these as sort of collimated cones of quarks and gluons. They're shown in the red and in the green cones here. And these are really useful for distinguishing the VBF Higgs to WW process because they're energetic, since they come right from a proton beam, and they tend to travel at a really small angle to the beamline, which tends to give them a high invariant mass. Then we make 2 kind of specific requirements to eliminate 2 of our main backgrounds, which is processes containing top quarks and processes with a Z boson decaying instead of a Higgs boson. And then we also make this requirement that there be no extra jets in between these 2 most forward jets. And this is just basically to exclude all of the really quark-heavy backgrounds of the LHC, since we don't expect extra jets in there. Finally, the spin zero nature of the Higgs causes the leptons that we're looking for to be preferentially emitted in the same direction, and this tends to be between the 2 jets, so we throw out any events that have leptons outside of those leading jets. And after applying all of these cuts, then we're left with a set of data that's enriched in our process of interest, VBF Higgs to WW process. But still, fewer than 1 in a billion collisions at the LHC produce Higgs bosons, and less than 1 in 10 of those happen via VBF. So resolving the VBF Higgs to WW process is challenging even after we place those cuts that select our signal. In the plot on the left here, we can see simulations of the expected physics processes that remain after those cuts, and the pie chart shows their relative amount. So you can see that the tiny orange sliver here is our signal. It's been magnified by a factor of 50 in the top plot so that you can even see it. Clearly, most of what we're left with is not Higgs to WW at all, but rather other physics events that we don't aim to study. So what can we do? To further separate signal from background, we use machine learning. Here we train a deep neural network, or a DNN, to distinguish signal from background. So the DNN is trained on simulations of signal and background, and it sorts the events basically according to their degree of resemblance to signal. It does this on the basis of 15 different input variables that target features of the signal and background events. 3 examples are shown here, where the distribution of our signal, again, is in the orange line. And then the distributions of all the background events that we don't necessarily want to see are shown by the colored bands. And you can see already that these variables offer good discrimination because they look quite different for our signal than for the expected backgrounds. Now, if we apply the DNN to the set of simulated events shown here, then we get the distribution that's shown on the right. So here events have been sorted according to their DNN score. Basically, the higher the score, the more signal-like the event. And you can see that for DNN scores above 0.94, now signal events dominate by a factor of 3 to 1, whereas before the DNN, they were swamped by a factor of 60. So that's really great because this excellent discrimination of signal from background allows us to perform a really sensitive measurement of the VBF Higgs to WW process. So basically we look at data recorded over the 3 years we talked about, We separate this data into 7 bins based on DNN score, and we do the same thing for simulations of signal and background events. This gives the distribution that you see on the left. In here now, just to remind you, orange corresponds to our signal, our 𝐉𝐵F Higgs to WW. Separately, as I mentioned, we apply cuts that target the 𝐺GF Higgs to WW process that we didn't talk about, but the observed distributions of those events is shown in red in the middle plot. For both of these plots, you can see that the bottom panel here shows the distribution of all of the data minus the background events. And in both plots, you can see that we have an excess of data over background, which means that we've managed to extract some 𝐺GF and 𝐉𝐵F Higgs to WW events. With this pure selection here, we can do a profile likelihood fit, which measures the cross-section of Higgs productions for both modes. Again, this basically corresponds to just how often a Higgs is produced by 𝐉𝐵F or 𝐺GF, and it's predicted by the standard model. The standard model prediction here is shown by this little red cross, and our measurement is shown by the black star. So within the measurement uncertainty, which is given by these brown or green contour lines, our measurement is consistent with the standard model. In addition to showing consistency with the standard model, this measurement also represents the very first observation of the 𝐉𝐵F Higgs to WW process in ATLAS. We've observed this process with a significance of 7 sigma. And what that means is that if there were no 𝐉𝐵F Higgs to WW production, there's only a 1 in 800 billion chance we get this result. So we're pretty sure. This precision is also an improvement of a factor of 2.5 over the previous analysis, which is nice to see. Now, the measurement that we just discussed reports the total cross-section for 𝐺GF and 𝐉𝐵F production, followed by Higgs to WW decay. But of course, we can't really see the total cross-section. We measure that cross-section in a region of phase space that we can actually observe. And that's defined by our detector geometric coverage, by its efficiency, by the analysis level cuts also that we apply to target Higgs events. To report this total cross-section, we naturally have to extrapolate from this subset of events that we observe to the entire phase space. And this extrapolation introduces some uncertainty. Namely, we have to rely on theory via simulations to tell us what's in between this phase space we actually observe and the total one for which we quote a measurement. Now, if we could reduce the extent of this extrapolation, then that would reduce uncertainty and increase our sensitivity. To do this, what we have to do is measure cross-sections only for the regions that we can actually see, or in practice, close to them. Measuring this kind of cross-section enhances sensitivity also to beyond the standard model physics effects, since it could be the case that beyond the standard model effects only show up in one part of the phase space and cancel out when we make more inclusive measurements. Okay, so how does this look in practice? For our 𝐺GF and 𝐉𝐵F Higgs measurements, we define subsets of the total phase space to which we have some amount of sensitivity. Then we try to measure a cross-section for each one. So for instance, for 𝐉𝐵F, we could first split by the number of jets. We could aim to measure a cross-section for events that have fewer than 2 jets and for events that have more than 2 jets. And then we could further split by the invariant mass of those jets and so on until we're left with many different cross-sections that we'll attempt to measure without extrapolating to the broader phase space. And here's how it looks when we do that. So bear with me and I'll explain how these plots look. So we define 11 of these different kinematic regions split by number of jets, PT of the Higgs, so that's the transverse momentum of the Higgs, and the invariant mass of jets. Then the measurement for the cross-section for each one is shown on the plot on the left, and it's divided by the standard model prediction. So basically points that fall on the line at 1 agree with the standard model. And then the bars give the measurement uncertainty along with kind of the colored bars. We generally see compatibility with the standard model. It's also nice to see that particularly for our 𝐉𝐵F cross-section measurements, which are shown with the orange box here, our measurement sensitivity is already competitive with the combination of all Higgs results from the ATLAS detector. And so that's all. We've seen that studying the Higgs boson with the ATLAS detector allows us to probe really interesting types of fundamental interactions that could help us to hone in on ways in which the standard model falls short. In particular, this measurement of the VBF and GGF Higgs to WW cross-sections is the most precise to date, and it shows good consistency with the standard model. But we're excited to keep making future measurements with an increasingly large data set and improving understanding of the measurement uncertainties, which will lead to even more precision tests of the standard model. Thank you.
Thank you very, very much. This was a very good presentation. Hence, many, many thanks for taking the time to really explain everything in detail. And to me, it's obvious that a huge amount of work was done to obtain all these results and, of course, to publish the paper. I do have a few questions. So, for example, when you mentioned the deep neural network, I was wondering which variables you use as input.
Yeah, for sure.
6, I think.
Yeah, definitely. Oh, maybe I should have asked if this is okay. Noeen, if I have backup slides, am I allowed to flip to them just because I have the distribution shown? Or
yeah, sure. You can use your backups.
Okay, cool. Thanks. So we'll just go for that. Just because sometimes it's nice to be able to sort of visualize the variables, that it's interesting to kind of see the difference between the signal itself and the background. Yeah, so we used a list of 15 variables. So probably more interesting than running through all of them is saying in general kind of how they were chosen. As sort of a first principle, there's kind of 3 different goals that we aim for, I guess. So one is suppression of background. So variables that tend to be really highly correlated with a particular type of background. For instance, this ET miss significance down here in the corner, you can see that the top background, which is in yellow, has a super different distribution than the signal. And this variable in particular is really effective at kind of discriminating signal from that particular very large background. Then the second thing is variables that are connected particularly to the decay of the Higgs boson. So to the kind of characteristics that are expected when the Higgs decays to 2 W bosons and then to 2 leptons. So I mentioned, for instance, that because of spin correlations, we expect that the 2 leptons kind of go off in the same direction, which means they tend to have a small angle between themselves. And so for that reason, we use variables like this one, which is delta phi LL, basically the angle between the 2 leptons. Okay, so we have kind of background suppression, Higgs to 𝐷𝑊, and then the next one is variables that target features really of the production mode, which is vector boson fusion in this case. So this is typically jet-related variables, so things that probe either the invariant mass of the jets or the angle between the 2 jets, and that provide us with kind of that extra handle on distinguishing the signal versus background. So yeah, these are the total variables, and those are kind of the guiding principles that were used when choosing them.
Awesome, thank you very much. I still have 1, 2 more questions. So on slide number 7 or 9, when you have somehow something in the Earth preselection level, but also when you go in the simulations, I was wondering actually how you estimate the background in your simulations, or at least the main sources of background.
Yeah, that's a good question. You're right, because to train the DNN rather, we exclusively, of course, use simulations, not data, which is kind of an interesting and unique feature of, I think, high energy physics, that we don't really have the data that we can train our neural networks on. So we entirely use simulations. So, I mean, there's many different types of kind of simulations that exist in the high energy physics world, of course. Most of them are based on, well, they're pretty much all based on Monte Carlo methods. So we use these simulations, but we need to make sure that they're, I mean, first of all, that we kind of capture all of the backgrounds that we would expect to have, and also just that these simulations do correctly model the way that data in real life is expected to look. So how we do this, kind of both of these goals at the same time, is usually defining using a slightly different set of cuts than the ones that we use in order to get to our signal region. We define a different set of cuts that kind of selects a different but similar phase space. And in that phase space, we compare the way that the simulations look to actual data in those regions, which are, I mean, I don't need to explain this to you, of course, but these are control regions. And so we use two control regions for this particular measurement. We have a top control region where basically we apply cuts that are designed to create a region that's really enriched in the top backgrounds, because as you can tell from this giant yellow slab, top processes are a really important background. And then we also have another region designed to target Z plus jets backgrounds, which are in green here. We have an almost control region for WW processes too, since those are an additionally large background, but it's not very pure. So essentially, yeah, we use these control regions to make sure that kind of our simulations look like the actual data that we expect. And then because we do see pretty good modeling as a function in particular of those 15 variables that we looked at, then we kind of trust the simulations and use them to train the DNN.
Perfect, thank you. Please, could you also comment on the sources of uncertainties in the most sensitive regions, thinking at slide number 10, for example?
Yeah, for sure. Yeah, thanks for remembering all of
and
this.
which are the dominant sources and how you plan to decrease these sources in future, for example, in the next version of the analysis?
Yeah, totally. The dominant sources of uncertainty for us are theory uncertainties, principally on the signal. So what this means is that, of course, we said that we use simulations to model backgrounds. We also use simulations to model the signal processes, and many calculations go into making these simulations. And the calculations generally are made with, they make use of some amount of approximation. And so this introduces some amount of uncertainty on the simulations that we use. We are very sensitive in particular to any simulations or any kind of sources of uncertainty that affect the distribution of jets in the VBF process. So principally, like, this is shower related uncertainties. So basically, in addition, of course, to having the hard scatter matrix element in the calculations, we also account for kind of extra emissions of quarks and gluons that happen. And those differences between different predictions there are by far and away the largest source of uncertainty for us. This is tricky. It's a kind of trade-off that happens, I think, often when you're using machine learning. We have a really good kind of way of excluding background from signal, but because the DNN uses so many variables to do this, small differences in simulations in each of those variables can add up and cause overall large differences between predictions. So I think one of the ways that we have to target this is to revisit the variables that we're using in our DNN, because they were decided upon before we kind of looked at this particular source of uncertainty, and try to find ones that are a little bit less sensitive to differences in principally shower predictions. Yeah, that's the largest source.
Okay, awesome. One last comment. What is your feedback or your idea on how a larger data set will improve the sensitivity of this analysis? Thinking at the end of run 3, when you will have 2 more data than in run 2.
Yeah, totally. So it will help already. Okay, so for this particular cross-section measurement that's shown on the slide here, where we measure the cross-section in many different bins, there we will, we're still limited typically by statistical uncertainty. For many of the cross-sections, the statistical uncertainty is shown in these kind of tan-colored bands, whereas the systematic uncertainty is shown in green. So for cases where the statistical uncertainty is larger than the systematic uncertainty, there we expect to see some improvement in precision with more data. The fact is, when we don't break this up into kinematic bins, and when we instead measure a single cross-section for GGF and VBF, there our largest limitations are really systematics related. So it's what we just talked about, where kind of differences in theoretical predictions and that sort of thing are the main kind of bottleneck right now. So I think it will be really interesting to keep doing measurements like this one in kinematic bins, maybe even in increasingly segmented kinematic bins with more data, because that's really where we'll stand to see improvement for run 3. And the kind of inclusive cross-section measurements that we at Atlas have been typically making won't benefit quite as much from the increased stats. So that's what we can target.
Many thanks again.
All right, yeah, thanks a lot. Very nice presentation and great result. So congrats for the result. I'll get started with a question on slide 4. So you've mentioned that you've concentrated on the second largest branching fraction of the Higgs decay. So why you did not pick the one with the largest one?
Yeah, that's a very natural question. So you can see here, so I guess first of all, it's helpful just to mention, if people aren't super familiar with this very complicated, messy, plot, that the black line here just indicates the mass of the Higgs boson as we know it. So it's really just anything along this black line that we're interested in. Oh, sorry, I have it here. Anything along this black line there. So yeah, the Higgs to WW branching ratio, meaning how often the Higgs decays to 2W bosons, is the second largest among all the decay modes. You can see that the largest one here is the decay to BB bar. So this is, of course, to 2B quarks. So the problem with this decay mode is that at the LHC, we have such a large quark and gluon background. Basically, we're colliding protons, which are themselves made of quarks and gluons. And so as a result, we really get a lot of processes that have that kind of composition. So we talked about the importance of distinguishing our signal from all the background processes. When we're looking at Higgs to BB decay, sorry, my headphones just died, no big deal. When we're looking at Higgs to BB decay in particular, that distinction between signal and background is a lot more difficult to make because so many processes resemble characteristics of the Higgs to BB decay. So that's really why we choose W bosons. We can use nice clean decay to leptons and not worry about the background so much. I'm just going to plug this in, sorry, and then make sure. Okay, perfect, I can hear, thanks.
Then you've showed the slide in the backup where you have all the distributions of the various input to the DNN. Which variable had the highest separation among all of the 15 variables?
Yeah, that's a good question. And this is a thing that we didn't probe specifically. So what we did do was, sorry, this is extremely slow. What we did was probe kind of different combinations of these variables. We were never, it's difficult to pick out, particularly with the DNN, because it learns so many correlations between the variables. It's difficult to attribute most of its separation power to any particular variable. So what we can say is that certain variables in combination were much better than other variables in combination. And yeah, I mean, one of the things I think that we particularly needed is we have these sort of variables that have kind of a funny name where it's M sub L1 sub J0. So basically the invariant mass of lepton and jet combinations. And we found that if we replaced these sorts of variables with instead ones that purely counted the number of jets or the number of leptons, the difference actually wasn't very large. So I guess what I'm saying is sometimes what you expect the DNN to kind of learn from one variable is different than what it actually learns. So yeah, we didn't unfortunately characterize a particular variable. This was just the most sensitive set.
So what kind of a metric did you use in terms of like choosing 15 variables versus 13 or 12 or even more variables?
Yeah, that's an interesting question. So we use basically a sort of crude bin by bin significance estimate. So I mean, this is obviously just a backup slide. It's a little bit messy, but I can walk you through kind of the general principles. I mean, essentially, we just look at the ratio of signal to background in all of the different DNN bins, and then also take into account the statistical uncertainty. And we played around with, these are sort of the different combinations of variables that were used. The interesting thing, I think, and the kind of pathway to improvement is that at the point where this DNN was trained, without having kind of experienced the large impact that systematic sources of uncertainty can have, we really only focused on maximizing the statistical only significance. Knowing now that particularly for signal processes, for VBF and for GGF, that the uncertainties on these processes really hurt us, I think a re-optimization could probably be done accounting for that as well. And so that would be a big kind of potential way to make gains, I guess.
Right. Yeah, so maybe if we go back to slide 6. I don't know. Yeah, can you say a bit about the slide after? Yeah. So there is a slight spike, right, around 0.6. Can you comment on this, or is this just statistical fluctuation?
Yeah, no, that's a very fair question. Yeah, totally. I see this here. Yeah. So this is a good question, and I'm trying to think if I know. It's almost, because it's a logarithmic plot, it's somewhat difficult to kind of tell what accounts for it. Okay, I guess what I can say is that, so I don't know for sure, we would never bin the DNN this finely exactly because of what you said, just that you get statistical fluctuations. What we do find is that for some, so all of these colored bands, of course, are simulated with Monte Carlo simulations. They're all, yeah, just simulations, not actual data, just for kind of people who haven't seen these plots. And what happens when these simulations are produced is that every kind of particle event in these simulations receives a certain weight, and that weight is designed to correctly populate the phase space of this process according to what it should be, can be to match data. And if you have simulations that are particularly low in statistics, then each of those events has to receive a really large weight to kind of in total make up the correct population of phase space. And this is something that we see particularly for our Z plus jet simulation. So if I had to speculate, I would say that it's due to a particularly large weight Z plus jets event. And those sorts of events are not they are not very physical, and ideally this is an effect that should be avoided. I mean, one of the things we're doing as an analysis team is trying to kind of provide input to get higher stat simulations. But yes, that was a long way of guessing, but that would be my educated guess.
Good. Maybe a last question on back on the systematic uncertainties. So you've mentioned from the systematics, the signal related uncertainties are the dominant ones. In terms of backgrounds, I mean, you have mentioned TT bar as being one of the dominant backgrounds. What's the impact on the systematic uncertainties from TT bar?
Yeah, that's right. TT bar is a dominant background. I guess the background composition, maybe I shouldn't have switched. The background composition changes somewhat interestingly when we go to the most sensitive high DNN region, and that's what's kind of shown here. So here it's in this region, it's really processes that most kind of closely resemble our signal. So in particular, we're really kind of hurt by the WW background once we look at that particular high DNN region. And because that region is where we kind of have most of our signal, it's most sensitive. So the main theory uncertainties, I guess, or like in general, the main systematics on the background that kind of get us are mostly WW and Z plus jets related. Even there though, the uncertainties are generally not a problem. They're pretty lowly ranked, I guess. It's really mostly uncertainties on the signal, on the, I guess, like theoretical uncertainties on the signal, and then to a lesser extent, experimental uncertainties, particularly that concern jets and the missing energy resolution, I guess. Yeah.
And for the miss ID, you also use Monte Carlo simulation, or was there a specific?
No, good point. Yeah, good point. No, I didn't mention that, but yeah, actually, so we have this background, this light blue labeled miss ID. So this is misidentified leptons. Yeah, so good question. We don't use Monte Carlo for that because it's known, of course, that in many Monte Carlo processes, the kind of chance that a jet is misidentified as a lepton isn't really very accurately reflected. So here we use a data-driven method. So basically we define a control region in which we make kind of slightly different selections to figure out the chance that a jet would be misidentified as a lepton, and we extract a certain factor from that. And then we apply that factor to another control region in order to get this background. So yeah, this is mostly a data-driven background.
Yeah, thanks. Great on this fantastic result. Thanks for the presentation.
Thank you.
These are all questions from Neda and Otilia. Or do you have more questions? No?
No, nothing from my side. I'm good.
Okay. I am muted. Okay. I didn't notice that I was talking and I was muted. Anyway, we have two questions in chat, and let me see. It's not my field, so if I'm pronouncing any word wrong, so I hope there is no problem, right? So
yeah, don't worry.
Okay. So first question is, what fusion is best to create and study the Higgs angled bound particle. I am not sure. It is angled bound particle. I don't know. If you guys
So
can
yeah,
read.
I can open the chat too, Noeen here. Yeah. What fusion is best to create and study the Higgs angular particle. So I am going to interpret this as asking what kind of production mode is best used to study the Higgs boson. So yeah, indeed, we did talk about different sorts, and like this is a fair question. Many of them have fusion in the name. So the two particular ones that we focused on today were gluon-gluon fusion and vector boson fusion. Best is a difficult question because all are good in their own way. So the gluon-gluon fusion process, which is one of the ones that we looked at, is the one that happens most frequently at the Large Hadron Collider. So it's the one that can provide us with the largest number of Higgs bosons, which is obviously a good point for it. There are many other production modes that have different benefits. So the vector boson fusion mode, like we talked about here, can probe different kinds of Higgs interactions with other particles. And then the same is true of other production modes. Basically, they involve the Higgs coupling with different particles. And so depending on what you're trying to look at, a different production mode might be the best one for you. So yeah, that would be my answer.
Okay, thanks, Robin. But can you please let me know what's the pronunciation of anglet bound particle, or what is it?
Yeah, I think this is, I think there might be some mistakes in the spelling. So I think it's Higgs brute. I think there's supposed to be an R in there. Yeah, but normally we would just call it the Higgs boson, which is fair. So the poor, I mean, yeah, lucky Peter Higgs, I guess, gets his name kept on it because it's too long to say all of those other names, as you have discovered.
Okay. Yeah. Okay, next question is, what about the muon that does not follow the predictions?
Okay, so I imagine this is referencing the muon G-2 anomaly, because if someone asks about the muon these days, then typically that's what they're interested in. So yeah, this is, I mean, good, yeah, good kind of general knowledge of what's going on in the field of particle physics, I guess. So our measurement doesn't really relate to this anomaly at all. So I guess for people who aren't familiar, there is a measurement of the muon magnetic moment, basically, that was done at a fully different experiment and institution. And it shows slight but significant disagreement with the theory prediction, which is exciting because it's not every day in particle physics that we actually detect some kind of disagreement with the standard model. This particular measurement isn't sensitive to that at all. All that we do really is use the muon to be able to say that we had a Higgs boson. So yeah, this measurement doesn't connect. There are certainly other kind of searches that are happening in this same experiment that are looking for processes that might be related to the muon G-2 anomaly. So mine, unfortunately, is not one of them. Judges can also feel free to comment on this if this is a little bit more their area. It's not so much mine, but yeah, this result anyway doesn't unfortunately provide us any insight into that very interesting anomaly.
Thanks, Robin. I think it was, I hope these questions were asked by David, and I hope he is also satisfied by this answer. But of course, he's not the one who is going to evaluate. It's the judges who are going to evaluate the answer. Right?
Well, thank you for the questions
that he's already having. So were the first people to predict the Higgs boson. Okay, so you said Edward Brout were the first people. Thanks.
Right, so with Higgs, I think, yes.
Yeah, it's not my field, but it's good to know. Okay, anyway. I will give it to now to our judges for closing remarks, and then after judges, Robin, you can give your closing remark, and then I will give mine. Thanks, everyone.
Well, it was a very interesting discussion, and of course the presentation was extremely well done and presented. I really think that overall you did a very amazing job. Congratulations, and of course, the good luck in the selection process.
Yeah, fantastic presentation. Well prepared, as Otilia said, and great results. So good luck with the rest of the steps throughout this competition.
Thank you very much, judges. It's always really nice to be asked questions about one's work and get to talk about it. And I really appreciate the insightful questions. And Noeen, I really appreciate the chance to do this. It was a lot of fun. So thanks so much. And thank you, audience, for being here and listening to me.
Okay, thanks everyone, and thanks to the wonderful judges. It was really a good session. Thanks for taking out time for this symposium, for judging our students. Like they are doing wonderful job. I have seen the previous talks and presentations that I was just thinking which were related to my category. My PhD research was not even that level. I was just a little bit like, oh my God, they're doing so good job. And Robin, your talk was really good, very well explained, not only presentation, but also all the questions during panel discussion as well as audience question and answers. With this note, I will share my screen. And okay, so, and then we will close the session. So if you would like to join in our future events, please follow us on Eventbrite, and you can see the list of upcoming sessions for symposium as well as other workshops and career development programs. And our next talk in particle physics is next week on August 18, 12 to 1 p.m. Pacific Standard Time. And our speaker is going to be Danica McDonald from University of Victoria, Canada. Please join us if you have time. And if you need to get more updates about Symposium, please visit our page. We update this page bi-weekly, and we also have a catalog where you can see the list of all abstracts who participated in this competition during the first round. And with this note, I will stop sharing my screen, and I think we can just close the session. Thanks everyone for joining us. Have a great day, great night, great afternoon from where you are joining. I think some are from UK, some are India, Belgium, as I remember. Yeah. So have a good night, good afternoon, good evening, and take care. Have a great day. Thanks for joining, and please join us again. Bye.
Thanks.
Thank you. Bye.
Bye.
Bye, Mintu, Majid, Cecilia, and Walter. Thanks for coming today, and please join us for the next week also.